Dear colleagues, this presentation is to give you an overview on the provenance analysis of white marbles in archaeology, on the methods used there, and I will put special emphasis on the use of ion chromatography in this issue. I have to put first a few remarks on the provenance analysis of white marbles in general. What are we basically doing? We have a sample of an unknown marble, for example, from a sculpture in a museum, white marble. And if it's of archaeological and art historic interest to know where this marble is coming from, we have a few possibilities to work in this line. Firstly, we have a different set or a large set of petrographic and mineralogical methods to analyze this sample. For example, petrographic methods, isotope analysis, EPR, electroparamagnetic resonance, trace element analysis, and especially what we are talking today, the analysis of so-called FIs, of fluid inclusions, small liquid inclusions in marble. But it's not enough to analyze the sample. Of course, we have to have a data bank. We have to compare our results with a data bank. And for this data bank, we analyzed approximately in the last 15 to 20 years, 4,500 quarry samples of marble from ancient quarries in the ancient world. Finally, we produced a large number of variables, a large number of results. You will see it later. Our data bank in the moment comprises is an Excel spreadsheet of 4,500 lines and 24 rows. So this big Excel spreadsheet you cannot evaluate with your eyes. You need a statistical data treatment, a suitable statistical data treatment, and there are different possibilities. This is not so important. We are using Statistica and SPSS. And with this statistical data treatment, we get hopefully a suggestion for the provenance or a match with the data bank and the provenance of the investigated marble. I will tell only two sentences of the major method. This is the isotope analysis. Petrography is a very nice method, but the petrographic features of the different marbles are sometimes very similar, and it's not easy to distinguish them. Isotope analysis is the major method. So far, EPR is out of fashion. Practically nobody's using EPR anymore. Trace element analysis is a very powerful tool, but this would be an own issue to talk about this. And our liquid inclusions in the marble we are analyzing with ion chromatography. Yeah, I told you about the data bank, and you can see here the series of trace elements we analyzed. There are many more. With ICP MS chemical analysis, spectrographic analysis. And here we have the variables we analyze with ion chromatography. Usually we express for different reasons. This is too detailed. I do not want to go into this detail. In the fractures of lithium over sodium, potassium, fluorine, chlorine, bromine, iodine. Iodine is a very powerful and very important element, and SO4. The stable isotopes of oxygen and carbon we are analyzing. Calcium carbonate is calcium CO3, so oxygen and carbon are major elements, and this is a tool and a method that is used in marble provenance analysis since 1972. The 1972, the first paper on this topic was published, and it's the standard. It's the state of the art, but it's not enough. You will see why we need additional methods. So one of the major issues we have to look is the samples. We have to have suitable samples. So there are different problems. Samples can be contaminated. Of course, we have to clean the samples. We cannot use sample powder. You cannot use a drilling powder from the bottom part of a sculpture or whatever. If you drill it with a household driller, you have a big contamination of all kinds of different elements. So we can use only small chips or grains of fragments taken from hidden parts or from the upper parts of our artifacts. These samples we have to clean carefully, especially when we talk now from ion chromatography. The important thing is if we touch the sample with our fingers, and we have to do this, we will get sodium on these samples, sodium chloride, and sodium is a very important element, and the method is so sensitive. So without cleaning, no serious results. Two slides on stable isotope chemistry, because this is the practically always done when doing provenance analysis of white marbles. The advantage is it's a widely used method. There are many labs available. You can buy the analysis there very cheaply. And yeah, this is the advantage of this method. The disadvantage you see here, if you plot your results from oxygen isotopes and carbon isotopes in the standard diagram, and you plot here your scattering of the data fields, I show you here only a few of the ancient, very important marble sites. You see here the Carrara marbles, for example. My last example will be on the marbles of Carrara, or the famous marbles from Pentelicon. Pentelicon is a quarry district, maybe 10 kilometers out of Athens, and was widely used from ancient times on. The biggest quarries are Prochaska, which is an island in the Marmara Sea near Istanbul, where most of the ancient marble was coming from. But you see here the problem. The data fields are overlapping, and if you make your analysis and plot it into this diagram, you have still a very wide choice. And so to bring it to the bottom line, it is not enough to analyze the stable isotopes, and we have to combine it with other methods. The other methods are trace element analysis, I told you before, but I will come now more to our ion chromatography and to the fluid inclusion analysis. We find these fluid inclusions in all crystalline rocks, also in quartz or whatever crystalline minerals we have, and also in marble. Marble is a recrystallized limestone. So it is a calcium carbonate which was metamorphosed in the course of its geologic history. So a limestone is usually a sedimentary rock, and due to tectonic activities and geologic processes, this formation suffers a so-called metamorphism. So it is subjected to higher pressure and temperature, and the limestone is recrystallizing. And we can see here a microscopic slide from one marble, and you can see the calcium carbonate minerals, and the fine-grained minerals here are small dolomitic grains. And when we zoom more, or when we look in the petrographic microscope, we have the possibility to look under polarized light, and we can see here the birefringence is the same picture under polarized light in the petrographic microscope. When we zoom more in, we can see a bigger magnification of the sample, or the same slide, and we can see here in the center a dolomitic crystal with a dull core and some clear rim. This is during the growth of the mineral, in the later stages, there were no more inclusions or only few inclusions in the rim. If we zoom further in, we can almost see or already see that this dull core consists of cavities that are filled with inclusion fluids. So this is the best magnification I got with the optical microscope. And you can see here the cavities, and in the cavities we can see gas bubbles. So this is filled with liquid, and there is a gas bubble. So we can extract this liquid simply by crushing the clean sample and extracting, opening these inclusions, and then analyzing these inclusions. Practically, it is done in a thoroughly cleaned agate mortar. We have here a few grains of this marble. We put 5 milliliters of triple distilled, very, very clean water on it. We grind it for a few minutes, and then we filter this liquid, and we can analyze this liquid and by ion chromatography. So this is called in earth science is the crush leach analysis of inclusions fluids. The method is a very specialized method, and not many labs are doing it, and I do not know any other lab except of ours who use this method for the provenance analysis of white marbles. So this is our equipment, our ion chromatography equipment, and I will tell you a few principles now. Very overview of ion chromatography. We have 3 important parts here in the assemblage of the method. We have to have a pump, a very special pump that is pumping a very regularly and homogeneous, that we do not see in the fluid stream any pump strokes. Then the heart of the whole machine is the ion exchange column. This is simply a tube, either glass tube or a plastic tube filled with a resin. And then we have some other not so important things. Then we have the detector that detects our result, and it is going to a printer or on the screen. The ion exchange tube is filled with resin, I said, and we have a large variety of resins. What is this resin doing? The pump is pumping a so-called eluent through the whole equipment. It is a stream of a carrier solution and regularly pumped through it. It's pumped through the exchange column, through the detector, and we can see on the printer or on the screen, we can analyze here the conductivity. The detector usually analyzes the conductivity of this eluent, and if we have no sample in it, it is, or it should be, an even line, the so-called baseline. We have here an injection port, and we have a sample here, and we inject a small amount of sample into this eluent, and it is the sample is pumped to the exchange column, and here the different component of the samples are held back in a different way. So, for example, fluoride, we see here in this diagram, we can see the so-called retention time. So the first element that is coming in this assemblage is fluoride, which is not held back in the column very much. It goes almost through with the eluent. And after 2 minutes or whatever, you can see that the conductivity is rising and falling down again. So fluoride passed the detector. A little bit later, 2 minutes later, chloride is coming, bromide, etc. So the different components of the samples are held back differently and accumulated in the column and then released simultaneously, and we can see the fall and the rise of the conductivity in our diagram. The beautiful thing of the ion chromatography is that we have hundreds or maybe even thousands of possibilities to adjust the machine to the needs of our samples, of our method, what we want to analyze. And we have many different eluents we can use, which has great influence. We can use many different columns and resins. The grain size of the resin here is important, of the filling of the column, etc. So when you want to establish a method, you have to work for several weeks. There is no cookbook. You have to work for several weeks to really get the system adjusted perfectly to the needs of your method. Okay, what we used or are using, we are analyzing anions with conductivity measurement, and in a special run, we analyze the iodide with a different sort of detection. And then we have a second machine for analyzing different or the main cations. I will show you the diagrams in the following slides. We are basically using a Dionex machine, ICS 3000, and the cations is still our old Dionex 120 for the cations. So this is the assemblage. Here we have the machine for the anions. This is the auto sampler. So you can load the sampler with maybe 50 or 60 samples. And this is the old machine, the small machine for the cations. A typical chromatogram is looking like this for the anions. And you can see here, for example, this stippled line here is the concentration of the eluent. We used potassium hydroxide as eluent, and starting with very low concentration. So the eluent has a low concentration. The elements, the different components of the samples are going through the columns almost like the eluent. And after, you see here, after 7 minutes, this is the injection time here. After 7 minutes, we have the first peak. This is a fluorine. This is a standard solution, and we know very well what we put into this standard in a special concentration. So fluorine is coming first. And then the major component of all these inclusions in the carbonates, but generally in the fluid inclusions, we have chloridic solutions, and chlorine is always the major anion. And so after 12 minutes or so, chlorine is coming, and then we are slowly increasing the concentration of the eluent to get also those nasty elements moved out of the columns that are sticking there into the columns. And we have here a very small peak. You see, this is bromine, a very important element for our application. We have nitrate, the peak of nitrate, of sulfate, and the last peak, phosphate, is the element that is coming as the last one. So we need a very high concentration to wash also the phosphate out of the column. And the machine is detecting the area of the single peaks, and we tell the machine the concentration of each peak. For example, 1000 ppb of chlorine in standard number 1, and in standard number 2, 5000 ppb, and 20,000 ppb in standard 3. We use usually a 3-point standardization. And automatically the machine detects then, or tells you, the concentration of your samples. The thing, what I told before, that you can adjust the system to your needs, in this case was the bromine. I wanted to analyze very low bromine concentrations, maybe 2, 3, 4 ppb bromine next to 5000 ppb chlorine. And in the standard applications that are given in the cookbooks, you start with the bromine was sitting here on the shoulder of the chlorine, and you have to adjust the concentration of your eluent and also the to have the correct columns to get the bromine away from all other elements that are there in higher concentration and may disturb your analysis. This is an example of the second run we are doing, the cut ions. We are analyzing lithium, which is a very important trace element in very, very low concentrations, but it's very sensitive, the method for lithium. So we analyze 0.1 ppb. This is just nothing in the fluid with very good reproducibility. Sodium is the major element, like chlorine in the anions. Sodium chloride is the major compound in this fluid, and potassium is also very important. We also analyze or can detect magnesium and calcium, but of course this is no wonder. It's a calcium carbonate with a high magnesium content, and there is usually also a little bit of calcium and magnesium in the sample, but this is of no diagnostic importance. You can also detect other elements, but here like strontium, barium or whatever, but usually these elements are in very low concentrations present here in these fluid inclusions, and it is better done with other analytical method. This is the chromatogram for iodide, which is like lithium, very, very sensitive. Fractures of ppb can be analyzed. So we have here this example here. The iodide is 0.3 ppb, and it gives still a very nice and trustworthy peak. So the detection limit is very, very nice. Yeah, here magnification of this peak, and you can see here already a little bit the noise of the background. So you always have to take care or look at this ratio. Usually we say 3 times the noise of the background is still a detectable peak. If the peak is slower and disappears in the noise of the background, then the error is much bigger. I'm coming to the end of the presentation, and I want to show you one application or one example of the use of the ion chromatography and the successful use and the enhancement of the discrimination when using these fluid inclusions. You know, for sure you have heard of the very famous Carrara marbles. Carrara is a district here on the northwestern coast of Tuscany in Italy. The Carrara quarries were mined for marble from Roman Republican times on, with practically no interruption or only small periods of interruption until now, and even today it's a really big quarrying area. You can see here a satellite image of the Carrara. Here's the town of Carrara, and the white patches here are not clouds on the satellite image, but these are the big quarries of Carrara. We have 3 valleys here in Carrara: Carrara Colonnata, Carrara Miselia, and Carrara Torano. These are different valleys or basins, it is called there, and all of these valleys are working still today and are producing marble. This was the most famous marble in medieval times. For example, Michelangelo used only Carrara marble. Here is the geologic sketch or map, and you see this blue colors are limestone formations. So these are very prominent, very thick limestone formations of Jurassic age. and it is a very fine-grained, a very white marble, and very widely used for artifacts, for sculpturing, but also for architecture. One of the problems that were interesting for us is to see if these marbles from the 3 different basins can be separated or can be told apart, that we can trace back an artifact to one of these locations, to one of these valleys. And an old publication from the times of this isotope analysis, carbon-oxygen isotope analysis, was by Hertz, and Hertz was one of the major specialists for this method, and they stated that these 3 different locations have the same isotopes and cannot be told apart. And in fact, you can see here that when using only the isotopes, the separation is not good. This table shows you the correct refinding of the samples from your database. So 77% of the samples we analyzed from Miselia are really falling into the Miselia field, or are close to the center of Miselia. 30% or 23% here are falling in other locations. In Colonnata, half of the Colonnata samples are misclassified, and even less samples from Torano are reconsidered as being Torano. So the rest is going to the other fields. So this is absolutely useless. When you come with an unknown sample, you can absolutely do not classify it or assign this safely to one of these 3 locations or valleys. When we use the isotopes, the stable isotopes, and when we use a large variety of trace elements, the correct refinding is already much better. Only 1 or 2 samples from Miselia are misclassified and to being Torano, etc. So this is already very useful and can be used. When we play all our cards and use also the results from the ion chromatography, you see here our ratios, lithium, chlorine, potassium, etc. We nearly get 100% correct reassignment. And you can now, with using all this method, you can now assign a Carrara sample from a museum to practically one quarry. This is the sample, the example I want to show you, are 2 examples. A portrait head from Vespasian in the Roman Museum Palazzo Massimo, close to Roma Termini. And the other sample we could analyze was from Toulouse. It was a portrait from Germanicus. And you can see here the statistical evaluation of the result. And we have the absolute probability of these 2 samples, or the relative probability. This is different aspects of probability. The absolute probability tells you how close the sample is to the average, to the center of this ellipse. We express our results in statistical ellipses, and with an absolute probability of 72 or 88, it is close to the center of the corresponding ellipse, and this is Carrara Torano. So these 2 samples are coming from the Torano Valley, and in fact Torano is the valley with the most frequent occurrences of the famous Carrara Statuario. That is the very white, spotless, flawless marble of Carrara. And it is always important when you do the statistical calculations to have also a second choice. The next, you have to have to provide it against the second possibility. And you see, only 11% is Carrara colonato and 23 Carrara micellia. So this is a fairly good result. If your result would be 88% or relative probability, 75% Carrara Torano and 71% Carrara micellia, then the result would be not a good one, and you could not use this. But here you can attribute it relatively safely. I'm coming to the end of my talk, and maybe an outlook or for the use of ion chromatography in this field is if you take your time, if you have the time to adjust the machine for other variables and other elements or whatever, you have a very, very wide field with the ion chromatography. Different carbonic acids, mono or dicarbonic acids, different cations you can use, and especially the modern applications, if you couple the ion chromatography with the ICP or ICP-MS, you can analyze different kinds of isotopes with a very, very small or low detection limits. So the possibilities here are endless. For this coupling with ICP-MS, for example, you have to have some pocket money of $1.5 or $2 million. Then you can establish a nice lab and can make really nice and new results. The nice thing of the ion chromatography is the variability of the method. I said repeatedly here, and in archaeology we had further applications. A very simple one would be soil investigation of ancient settlement areas. You can simply take an auger, take soil samples, wash this in triple distilled water and analyze the water for nitrate or phosphate, which are very safe indicators for a settlement. So you can really make a nice prospection and define, for example, settlement areas. Okay, I hope I gave you a short overview on this. Thank you very much and goodbye. Ciao.